Kalispera. Good afternoon. I'm Tassos Anagnostopoulos, Principal Solutions Architect at Unisystems, and I'm going to present to you a case study regarding how we modernized a legacy system at a banking institution using open source technologies. So we're going to start with the presentation of the case. So what were the drivers and the goals? The business and technological constraints that govern the project. We're going to present both the existing architecture and the target architecture of the bank. We're going to be looking at the open source components that were employed in our solution, discuss a little bit the implementation approach and the challenges, and finally look at the impact of the changes caused by the introduction of the open source technology. So, what was the case? We have a large European bank that had a legacy core banking system, and they realized that they need to change. The main reasons for this change were, first of all, they needed a modern user interface for their end users. So they were still using interfaces from the 80s, C++ and Power Builder based. They had a system that was very difficult to maintain. So because they needed to have resources for languages and technologies that were old, and every change that they were introducing was very, very difficult to test. They had very long release cycles. So the business would come and say, we need something new, and the response would be, okay, let's try to put this in the next release, which is 4 or 5 months down the road. That is something that is not acceptable anymore in today's very fast evolution of things. And along with that, they had to meet increasing requirements regarding digital and mobile, something that what is called digital transformation. Without this, you cannot go far. So, the challenges. Their existing infrastructure was client-server, so something that is very, very old-fashioned and monolithic. So there was COBOL code that had most of the logic. It was not just transactional logic, but it was entire business logic inside COBOL programs. And then the remaining part of the logic, the more UI-related logic, was installed on the client PCs. Okay, so we're talking about architecture from 70s, perhaps 80s. COBOL, regarding COBOL, we know that it's something that after Y2K, it's very difficult to find such resources, but the bank still has a high dependency on them. It's very difficult to test changes due to this technology, and also because there are no tools that allow you to test when you're using a very legacy approach to implementing code. And as we said, a very slow delivery cycle. So this is something that business found unacceptable. So, what were the project goals? First of all, introduce a multi-tier architecture, which should be loosely coupled. So we should be able to make changes in one tier without grossly affecting the other ones, so that we can have independent teams working. Employ latest technologies. Okay, not only move away from C++ and COBOL to an extent that this is possible, but try to be at the niche, because if you don't do that, then very, very soon you will fall behind. Another big problem, and it's something that many of you may have seen, when you work in large systems, because you are afraid that when you touch something, you may break something else. Instead of, when you want to make a change, you just copy and paste the code and create something else that's a little bit different from what you had initially, but you don't try to refactor. You just have 2 copies, and then you're safe that what you changed only affects the new functionality, but you don't have to go back and do the regression testing on the other stuff. And it's something that's understandable when you have something that's legacy. But now there are tools when you have new technologies, there are tools that can help you get past that. Another important thing is the visibility into the business logic. So in the existing architecture, the bank had some logic on the client, inside the COBOL programs, inside database, stored procedures, and it was all hidden. And the business had no way of knowing what is running, and why it's running, and where it's running. And if you want to make a change, you didn't know exactly where you have to go to make this change. And no matter how much documentation you have, it's never up to date. So you actually depended on the developer to tell you what is the exact business logic that's inside the system. And as we said, there are also shortened release cycles. So what was the focus of the project? You cannot do everything at once, okay? So ideally, when you introduce new technology, you also want to re-engineer your business logic so that you can kill two birds with one stone. But since we're talking about we're talking about the core banking system of a bank, trying to change everything at the same time is bound to create issues, and you are bound to run into trouble. So what the bank decided to do is to do a pure technological upgrade to the extent that this is feasible without introducing a new business logic. Also, the goal of the bank is to establish something that can be used by all the channels. So we're talking about internal employees, people at the branches and headquarters, but also customers, okay? Mobile banking, e-banking, stuff like that. Again, they said, okay, let's keep it a little bit smaller. Let's focus on the internal employees first, on the applications that are used by the internal employees. And then next phase, we'll also look at going e-banking and mobile banking. Very important is to extract the logic, the business logic from wherever it is and bring it into a central location using business rules. I'm going to talk about this a little bit later on. And one of the most important decisions that they had to make was what to do with their mainframe system. So one would tend to say that, let's get rid of this. It's technology from the 70s, but it has some very, very strong points. It's extremely fast, plus there is a database structure in it. It's hierarchical, and if you try to get rid of this and change it with something else, again, you're opening up the scope of the project so much that you're bound to fail. So what they said is, okay, let's keep the mainframe, but let's take these monolithic transactions that do everything from beginning to end, and let's split them into small modules and have these modules do very, very specific things, okay? So where initially you would have a transaction that would say, for example, debit an account, so do a withdrawal, and that transaction would have to do everything, all the checks from beginning to end. So, for example, what is the type of transaction? Is it a term deposit? And if it's a term deposit, are you allowed to do a transaction this specific date? Is it an overdraft account? If it is, then you may be allowed to go over your credit limit, over your limit. So even if you have zero funds, you may be able to withdraw. If you're trying to do a large withdrawal, you may need the approval of a manager. All this logic was inside a mainframe application. So all this was split in small chunks, components, which are reusable, and then these were left in the mainframe system for speed and also for backwards compatibility, but all the integration was moved out of the mainframe system and put into a middleware, which we'll see in the next slides. Constraints of the project. An important one is that it has to be completed in 3 years, which may seem like a long time for some of you, but for such a project, it is not. Major constraint is coexistence with the old system. So at all times, you have to maintain backwards compatibility. That's a big pain. It's necessary because you cannot go big bang. You cannot just create your system and one day turn the switch and say, tell everyone, here are the new transactions. You cannot do this when you're talking about the core banking system. So you have to do partial rollouts. But when you do partial rollouts, it means that some things are going to be done with the old system, some things are going to be done with the new system. So at all times, you have to be backwards compatible. And also, there were some technological choices that were dictated from the existing expertise of the bank. So you will see in later slides that the architecture is a combination of Java and .NET. And the reason for that is that the bank had some .NET expertise, and so they wanted to leverage that. And there were some applications that were already built using .NET. Then again, for some other parts of the system, it turned out that Java was a much, much better choice. So let's take a look at the initial architecture. At the heart of the system, we have a mainframe with a relational database in it. And we have users at the branches, also in the headquarters, but most of the users are at the branches, that they connect directly to the mainframe. It's what I said, it was a client-server technology. Okay. Additionally, each branch had a local branch server where they would be keeping some static data. For example, what were the currency exchange prices and stuff like that. So that anything that could be cached locally, the applications wouldn't have to go to the mainframe to get it. And of course, the branch server would get these values from the mainframe whenever they were changed. Now, in addition to that, because a bank doesn't have only one system, the bank also has some other peripheral systems, they had built a custom integration hub. And when a transaction required that other systems were engaged in the transaction, then what would happen is that, again, the client applications would be calling the custom integration hub, and then the hub would coordinate, would call all the external systems and the mainframe and return the result to the client. It's a very high-level depiction of the architecture so that you get the gist of what we had to deal with. So, moving on to what we decided to build instead. We have the internal users, which can be very light PCs, so we don't need to install anything on them. It's only a browser-based front end. In addition to the internal users, we have also the external users, so customers, which may be coming through a PC or a mobile device. And on the other side of the picture, we have the mainframe, but we also have all the other systems of the bank, and also some external systems, for example, credit bureaus that need to be contacted as part of a transaction. And we introduce a middleware layer. Middleware layer that we're going to see in detail in the next slides, which includes a caching mechanism, similar to what the branch servers were doing, but also very important, a centralized logging, something that allows us to have a very good visibility into what's going on in the system. So all the machines, all the clients are accessing the mainframe. There is no direct access to the backend systems. And then the mainframe knows how to coordinate everything. Let's take a look at the technology overview. So far we've been talking very theoretically. At the bottom, of course, we have the mainframe layer, and we also have all the other internal and external systems of the bank, the backend applications. In the middle, we have the middleware layer. In the front, we have a web app for the employees of the bank, and we have another set of web apps. We have a web app for the customers, for our e-banking application, and we also have mobile app services to support the mobile apps. Okay. However, what was seen is that although ideally you should be able to have a middleware that can service all the front ends, there is lots of logic that is channel dependent. When we say channel, we mean internal employees, customers, and so forth. And that each channel needs a lot of services that there's no point in that they do not need to belong to the middleware layer. And it's a much better fit if they are sitting somewhere separate. So the channel layer was introduced. In addition, there is another type of customer, fintechs, financial technology companies. You may be aware of the Payment Services Directive, the second version, PSD2, which imposes to banks that they expose an API allowing customers to become self-serviced through third-party applications. So basically, each bank has to open up their systems through APIs. So to satisfy this need, there's also an API management layer and, of course, a corresponding channel for this API. Looking at the actual technologies, so at the mainframe layer, of course, we're talking about proprietary. The middleware layer is Java. The channel layer was chosen to be .NET Core. And on the web app layer, ASP.NET Core MVC was used together with AngularJS. So I assume that most of you are familiar with .NET Core and Angular. There's not much point talking about this. So what I've decided is to focus on the middleware layer, where it has some quite interesting technologies involved. They are all Java-based. So if we look into this in more detail, we have integration services, business rule management, business process management, distributed cache, an application server underneath, and also the logging services. So, integration services. What is an integration service? Many of you will think of an enterprise service bus, okay, which is the traditional way of approaching a problem like this. So you have all the backend systems connecting to an ESB and all the clients talking to the ESB. It's one big centralized thing. Well, this is kind of old school. So let's take it again and see, but try to be a little bit more, try to be minimalistic. What is an integration service? It's something that manages to take a message from a sender and deliver it to a receiver. Of course, you may have many senders, many receivers, you have lots of protocols to worry about, and you may have many complex rules. So you take the message A, and it has to go to receivers A and B. But sometimes message B, and then you have message B, which should go to receiver C only as XML. But then translated, sometimes it may need to be enriched. And then depending on a condition, you may need to send it somewhere else, but in a different format. So in general, you need to be able to cater to needs such as translation of protocols, gluing components together, defining routes, so what goes where, filtering, so not all the messages should be processed, and you also have some non-functional requirements, such as location transparency, so sender shouldn't know where the receiver is, and of course concerns like high availability. All this should be taken care by the integration service. So, the approach that was used in this project is Apache Camel. Some of you may be familiar with it. So, in the simple example that I have here, you have a JMS queue where you have messages arriving, and you have a router, And that router has a very simple logic. It says that if we're talking about a comma-separated value message, then I want you to send it to an FTP folder, to an FTP site. If it's an XML message, then I want you to put it into another JMS queue. How do you do all this? You can do it graphically, but Camel supports domain-specific languages, and there's one for Java. You can also do it in XML. So here you can see the example in Java. And it's very simple. You just say from, where you start, and then you list the components one by one, so you have a choice. And when your file name ends with XML, then you want your message to be sent to a JMS queue, which is called XML messages. If it ends with CSV, it goes to an FTP. So Apache Camel is a framework that allows you, basically it consists of endpoints. Endpoints is what you call, and also what sits at the end of the routes. And then these are supported by components. So components explain to Camel how they should interact with the various external systems. And you build your flow using processors. So a combination of endpoints, components, and processors allow you to define any custom logic. To give you an understanding of what can be achieved, in this diagram you see some integration patterns. There's a book called Enterprise Integration Patterns. These have been kind of coded so that there is a common vocabulary and notation for describing integration solutions. And here you see some of the most common ones. So there are more than 60 such patterns, that are defined in this book, which is called the Bible of integration patterns. And they are supported in Camel out of the box. But of course, one can go and create custom processors, and that's something that we had to do in order to talk to the mainframe. So there's no component that, there's a component to talk to JMS, to FTP. There was no component to talk to the mainframe, but we built one. So that was about integration. The other pillar in the middleware was business rule management. So what is business rule management? Every application has business rules. Every organization has business rules. And these business rules can be in code, so if, else, if, stuff like that. They can be in stored procedures. They can even reside in spreadsheets, Excel. So it's very, very difficult to be able to understand, for a business person, to be able to understand what the system does. Okay, there may be documentation, but how are you sure that the system does what it's supposed to do? So one of the technologies that is used is called business rule management, BRM, where you take all the rules, you extract them from the various systems, and you put them in what is called a rules repository. How do you do that? We'll see in the next slides. But once you do that, once you have all your rules centralized, then you can give your users, and your users can be not only developers, but business users. You can give them a tool where they can go and both write the rules, but also be able to see the rules and test them. And then, of course, this is at design time, and at runtime, you have a rule engine that provides the execution. So the rules run inside your rules engine, and they are not coupled, they are not tied, hard-coded into your application. So one such system, a business rule management system, is Drulls, which is an open source solution. And it consists of a web UI for managing the rules and authoring them. There's a runtime engine, which is Drulls Expert. And it has two extensions, which I'm not going to cover here, but they are very, very useful for complex event processing. So if you want to be able to take real streaming data that are coming in and make decisions based on that, something that is time sensitive. And also if you want to be able to do automated planning, so for example, you have, say that this conference had many, many rooms, and you wanted to allocate the best way to allocate which session should go into which room, depending on what people want to attend. So you basically you do optimizations of this sort. Writing business rules. So a basic primer on what is a business rule. So basically you have a rule, every rule has a name, and it has some attributes. It's basically the elements, the entities that it's going to work upon. And then you have a when and a then. It's like an if statement, but with no else. And the fact that there is no else is very important. And then you have, for lack of a better word, you have the left-hand side, which is what's the if, and then you have the right-hand side, which is what happens if the rule is satisfied. To give you an example, when there's a fire, turn on the sprinkler. And also when the fire is gone, turn off the sprinkler. So you can see we have two elements here, the fire and the sprinkler, and we operate on the room, on many rooms. And then if some conditions are met, if there's a fire in the room we tie the fire with the sprinkler through the room, and then if the sprinkler is not on, then turn it on. Then again, if the sprinkler is on, but the fire is not there anymore, then we go and turn off the sprinkler. So it's not something that is procedural. Okay, you can have many rules, and the system is going to examine all the when conditions and only choose the ones and then execute the ones that satisfy the when condition. That's why there is absolutely no point in there is never an else, because it's not that we're evaluating one rule. You may have 100 rules, and then the system just checks which ones should be applied, should be executed. How do you write business rules? Well, one approach is what you saw before. It's called decision. For rules, it's called a rules language, DRL. But for business users, you can have spreadsheets, Excel spreadsheets. You can have decision tables inside the rules. You can have a guided rule editor where you can have many complex rules, but the business user does not need to understand the DRL. They can just go and put in the values that they want. You can also have rule templates. We talked about DRL, and you can even create your own custom domain language. Moving on, the third pillar, business process management. BPM is about improving corporate performance. That's a very theoretical approach. Corporate performance by automating business processes. So typically, when we talk about BPM, we are talking about, first of all, understanding what the process is about, defining the process, designing, executing, and monitoring. So it's a cycle, and it feeds back in the sense that when you monitor your process, then you understand what improvements you need to make, and then you have a next cycle. There is there's a business process management notation that is used for depicting business processes, and that's called BPMN. And sorry, it was a 45-minute presentation.
Okay. We just need to synchronize with next door. They want to start at 4:45.
I know.
Okay.
Okay, I'll try to accelerate, but there's...
Thank you.
Okay. So what I was saying is that, so you have your process design that is that is depicted through this business process management notation. And you have steps, and these steps can be manual or automatic. And usually your complex decision logic is implemented via business rules, what we saw before. So for BPM, what we used was JBPM, which is a lightweight workflow engine written in Java that allows you to model your process in BPMN and execute them. It's preferred because it allows you to, it caters to both business and technical users. So it has UI that's understood by the business and also allows you to go very deep in the technical side. And it has all the dynamic and adaptive features that are needed in order to be able to model real-life complex situations. So I have some screenshots of the JBPM designer here and how you model your forms. And also there's an Eclipse plugin that allows you to do development using JBPM. Moving on, distributed cache. The proper term for that is in-memory data grid. So it's basically a very fast key value store that is distributed. Okay, NoSQL solution provides very, very fast access to data and supporting not only read but also write operations. So it's something that's it's a key part of any enterprise solution where you have lots of static data involved. For the solution, for the particular architecture, we chose InfiniSpan, which is a distributed cache solution, which has advanced functionalities such as transactions, events, distributed processing, geographical failover, and stuff like that. It is Java-based, but it's also available as a language-independent service over a REST interface. And it integrates with Spring, JPA, and many, many more frameworks. So, we talked about all these open source, nice open source tools, but we are in the enterprise, okay? And the bank was not opposed to using open source technologies, but they said, okay, wait a minute, are you sure that all these products are certified to be enterprise ready? And I need 24/7 support, okay? I have a core banking system here to support, and you're coming to me with open source technologies. So the answer to that is, okay, well then I'll give you something that has all the good things of open source, but also with all the support that comes from a productized solution, such as the JBoss middleware, which is supported by Red Hat. So if we look at the product mapping, then at the bottom layer, we have the application server. It's Wildfly. Perhaps you saw the presentation by Mr. Andreadis earlier on. So in the Red Hat world, in the productized supported version, that's the JBoss EAP. Then we had Apache Camel, which is Red Hat JBoss Fuse. We had JBPM and rules. These are combined in one product, which is the JBoss BPM suite. And we have JBoss Data Grid, which is the supported version of InfiniSpan. Logging, that was the last thing if you remember on the middleware. It's an ELK stack, and it consists of three things. So it's a database itself, which is Elastic. And by the way, there's a presentation tomorrow on Elastic, so if you're interested in logging, you may attend that. So it's a distributed database, it's document-based, it's NoSQL database designed to allow very, very fast searches. Logstash is the ingestion mechanism, so it's what pulls things from the logs and puts them in Elastic, but it also parses them using a pipeline so that they are nicely split into chunks that Elastic can understand. And then there's the UI, which is Kibana. So it's a plugin that gives you interactive data visualization capabilities. I have a screenshot here of Kibana so that you can see some of the features. For lack of time, I'm not going to go into that, but if you are interested in the logging, I do encourage you to attend tomorrow's session. It's not by me, but I saw that it's in the schedule, and I think it's definitely worth attending. So, slowly wrapping things up. What was the implementation approach that we used? There were a total of 4 streams. There was the front end that was dealing with a UI experience. There was the back end that was decomposing the monolithic mainframe transactions. And the middleware, which was everything that I showed you, plus an overarching stream that was the architecture, making sure that the other 3 streams are aligned. And of course, this is, we had an as-is architecture and targeting the desired architecture. And there are also 4 stages. Okay, analysis, design, building, and testing. Okay, nothing new here. Don't take this as being a waterfall approach. So these are just, that's why I call them stages, not phases. So it's the steps that each transaction goes through, each of the mainframe transactions goes through in order to be reverse engineered, decomposed, redesigned, built, and tested. And of course, we have the program and project management like any other project. Application lifecycle management, I am not going to go into this in detail. Anyway, you'll have the slide decks, so I'm just mentioning here all the tools that we used. We tried to be open source as much as we could. In some cases, we saw that there were some other tools that were not open source that were available. So, implementation challenges. Well, it may not be very apparent to you, but reverse engineering, because that's what we did, of an existing core banking system is an extremely complex and arduous process. And besides everything else, you need to be able to trace all the requirements and make sure you haven't missed anything across all the levels, all the layers of the system, and you have to do exhaustive testing. Nothing can go wrong when you have a banking system. You cannot have a bug, and start missing money. And also, the introduction of multiple new technologies resulted in a significant learning curve. So there was a slow start to the system. So, expected impact of change. I say expected because this project is still going on. So we're somewhere in the middle. And there's a pilot that's going to be delivered in a couple of months. Easy prototyping of new business requests. Now business, when they require something, when they envisage something new, they can actually get a feel for it, and they don't just have to write it on paper and wait for 4 or 5 months before they see something. And that's because of much shorter release cycles, but also the versatility of the UI tools. As we said, centralization of business logic, alignment with the BIAN standards, Banking Industry Architecture Network, standards, which allows the bank to talk the same business language with other banks, so it's much easier to integrate and exchange messages with other banks. And a system that's much more easily maintained because it's decoupled. Most of the technologies are much more recent, much easier to work with. We have managed to automate the development and the testing processes, so automate the builds and everything that you would expect from a modern development project. And very important, this paves the road for moving to the next step, adopting containers and actually managing to become a truly DevOps organization. So I take it, we don't have, I don't know if we have time for questions.
Of course we do. We have time for 3 questions, guys, before we join everybody else for the closing keynote for today. Questions? no question?
Yes, one question.
Okay. How many years has this project been going on? When did it start?
It started about 1.5 years ago. So we're somewhere in the middle. Of course, one is always optimistic. So the 3-year duration is proving to be a little bit short. But yeah.
Can I ask one question?
Yes.
So what is the process of migrating the data from Iraq from data?
There is, okay, so I don't know if you heard the question, what's the process for migrating the data? There is, perhaps I didn't make it clear enough, there is no data migration. That's why we're keeping the mainframe, because if we would try to also migrate the data, it would be, we would be trying to do the impossible, and we would fail. So we're keeping the mainframe, we're keeping the hierarchical database as it is, but we're extracting all the business logic, so we're increasing significantly the maintainability. But there is no migration. Okay.
Any more questions before we wrap it up? Tasso, thank you so much.
Thank you.